VHDL is a hardware description language used in electronic design automation to describe digital and mixed signal systems such as field-programmable, gate arrays and integrated circuits. VHDL can also be used as a general-purpose parallel programming language. History: VHDL was originally developed at the behest of the U.S. Department of Defense in order to document the behavior of the ASICs that supplier companies were including in equipment. The idea of being able to simulate the ASICs from the information in this documentation was so obviously attractive that logic simulators were developed that could read the VHDL files. Due to the Department of Defense requiring as much of the syntax as possible to be based on Ada, in order to avoid reinventing concepts that had already been thoroughly tested in the development of Ada, VHDL borrows heavily from the Ada programming language in both concepts and syntax. The initial version of VHDL, designed to IEEE standard IEEE 1076-1987, included a wide range of data types, including numerical, logical, character and time, plus arrays of bit called bit_vector and of character called string. A problem not solved by this edition, however, was multi-valued logic, where a signal's drive strength and unknown values are also considered. This required IEEE standard 1164, which defined the 9-value logic types: scalar std_logic and its vector version std_logic_vector. The updated IEEE 1076, in 1993, made the syntax more consistent, allowed more flexibility in naming, extended the character type to allow ISO 8859-1 printable characters, added the XNOR operator, etc. Minor changes in the standard added the idea of protected types and removed some restrictions from port mapping rules. In addition to IEEE standard 1164, several child standards were introduced to extend functionality of the language. IEEE standard 1076.2 added better handling of real and complex data types. IEEE standard 1076.3 introduced signed and unsigned types to facilitate arithmetical operations on vectors. IEEE standard 1076.1 provided analog and mixed signal circuit design extensions. Some other standards support wider use of VHDL, notably vital and microwave circuit design extensions. In June 2006, the VHDL Technical Committee of Accelera approved so-called Draft 3.0 of VHDL 2006, while maintaining full compatibility with older versions. This proposed standard provides numerous extensions that make writing and managing VHDL code easier. Key changes include incorporation of child standards into the main 1076 standard, an extended set of operators, more flexible syntax of case and generate statements, incorporation of EHPI and a subset of PSL. These changes should improve quality of synthesizable VHDL code, make test benches more flexible, and allow wider use of VHDL for system-level descriptions. In February 2008, Accelera approved VHDL 4.0, also informally known as VHDL 2008, which addressed more than 90 issues discovered during the trial period for version 3.0 and includes enhanced generic types. In 2008, Accelera released VHDL 4.0 to the IEEE for balloting for inclusion in IEEE 1076-2008. The VHDL standard IEEE 1076-2008 was published in January 2009. Standardization: the IEEE standard 1076 defines the VHSIC Hardware Description Language or VHDL. It was originally developed under contract F3361583C1003 from the United States Air Force, awarded in 1983 to a team with Intermetrics, Inc. as language experts and prime contractor, with Texas Instruments as chip design experts and IBM as computer system design experts. The language has undergone numerous revisions and has a variety of substandards associated with it that augment or extend it in important ways. 1076 was and continues to be a milestone in the design of electronic systems. Revisions IEEE 1076 to 1987, first standardized revision of R7.2 of the language from the United States Air Force. IEEE 1076 to 1993, significant improvements resulting from several years of feedback. Probably the most widely used version with the greatest vendor tool support. IEEE 1076 to 2000 minor revision introduces the use of protected types. IEEE 1076 to 2002 minor revision of 1076 to 2000. Rules with regard to buffer ports are relaxed. IEC 61691-1-1 to 2004. IEC adoption of IEEE 1076 to 2002. IEEE 1076 to 2008 major revision released on the 26th of January 2009. Among other changes, this standard introduces the use of external names. IEC 61691-1-1 to 2011. IEC adoption of IEEE 1076 to 2008. Related standards IEEE 1076.1 VHDL analog and mixed signal. IEEE 1st of January 1076 VHDL AMS standard packages. IEEE 1076.2 VHDL math package. IEEE 1076.3 VHDL synthesis package. IEEE 1076.3 VHDL synthesis package. Floating point. IEEE 1076.4 timing. IEEE 1076.6 VHDL synthesis interoperability. IEEE 1164 VHDL multi-value logic packages. Design. VHDL is commonly used to write text models that describe a logic circuit. Such a model is processed by a synthesis program only if it is part of the logic design. A simulation program is used to test the logic design using simulation models to represent the logic circuits that interface to the design. This collection of simulation models is commonly called a testbench. VHDL has constructs to handle the parallelism inherent in hardware designs. But these constructs differ in syntax from the parallel constructs in Ada. Like Ada, VHDL is strongly typed and is not case-sensitive. In order to directly represent operations which are common in hardware, there are many features of VHDL which are not found in Ada, such as an extended set of Boolean operators including NAND and NOR. VHDL also allows arrays to be indexed in either ascending or descending direction. Both conventions are used in hardware, whereas in Ada and most programming languages only ascending indexing is available. VHDL has file input and output capabilities, and can be used as a general-purpose language for text processing. But files are more commonly used by a simulation testbench for stimulus or verification data. There are some VHDL compilers which build executable binaries. In this case, it might be possible to use VHDL to write a testbench to verify the functionality of the design using files on the host computer to define stimuli, to interact with the user, and to compare results with those expected. However, most designers leave this job to the simulator. It is relatively easy for an inexperienced developer to produce code that simulates successfully but that cannot be synthesized into a real device. or is too large to be practical. One particular pitfall is the accidental production of transparent latches rather than D-type flip-flops as storage elements. One can design hardware in a VHDL to produce the RTL schematic of the desired circuit. After that, the generated schematic can be verified using simulation software, which shows the waveforms of inputs and outputs of the circuit after generating the appropriate test bench. To generate an appropriate test bench for a particular circuit or VHDL code, the inputs have to be defined correctly. For example, for clock input, a loop process or an iterative statement is required. A final point is that when a VHDL model is translated into the gates and wires that are mapped onto a programmable logic device such as a CPLD or FPGA, then it is the actual hardware being configured, rather than the VHDL code being executed, as if on some form of a processor chip. Advantages. The key advantage of VHDL, when used for systems design, is that it allows the behavior of the required system to be described and verified before synthesis tools translate the design into real hardware. Another benefit is that VHDL allows the description of a concurrent system. VHDL is a data flow language, unlike procedural computing languages such as BASIC, C, and assembly code, which all run sequentially, one instruction at a time. A VHDL project is multi-purpose, being created once. A calculation block can be used in many other projects. However, many formational and functional block parameters can be tuned. A VHDL project is portable, being created for one element base. A computing device project can be ported on another element base, for example VLSI with various technologies. Design examples. In VHDL, a design consists at a minimum of an entity which describes the interface and an architecture which contains the actual implementation. In addition, most designs import library modules. Some designs also contain multiple architectures and configurations. A simple AND gate in VHDL would look something like import std_logic from the IEEE library IEEE, use IEEE.std_logic_1164.all. This is the entity ANDGATE is port, end entity ANDGATE. This is the architecture RTL of ANDGATE is begin O less than equals I1 and I2, end. Architecture RTL. While the example above may seem verbose to HDL beginners, many parts are either optional or need to be written only once. Generally, simple functions like this are part of a larger behavioral module, instead of having a separate module for something so simple. In addition, use of elements such as the std_logic type might at first seem to be an overkill. One could easily use the built-in bit type and avoid the library import in the beginning. However, using this 9-valued logic instead of simple bits offers a very powerful simulation and debugging tool to the designer which currently does not exist in any other HDL. In the examples that follow, you will see that VHDL code can be written in a very compact form. However, the experienced designers usually avoid these compact forms and use a more verbose coding style for the sake of readability and maintainability. Synthesizable constructs and VHDL templates. VHDL is frequently used for two different goals: simulation of electronic designs and synthesis of such designs. Synthesis is a process where a VHDL is compiled and mapped into an implementation technology such as an FPGA or an ASIC. Many FPGA vendors have free tools to synthesize VHDL for use with their chips, where ASIC tools are often very expensive. Not all constructs in VHDL are suitable for synthesis. For example, most constructs that explicitly deal with timing, such as wait for 10 nanoseconds, are not synthesizable despite being valid for simulation. While different synthesis tools have different capabilities, There exists a common synthesizable subset of VHDL that defines what language constructs and idioms map into common hardware for many synthesis tools. IEEE 1076.6 defines a subset of the language that is considered the official synthesis subset. It is generally considered a best practice to write very idiomatic codes for synthesis, as results can be incorrect or suboptimal for non-standard constructs. MUX template. The multiplexer, or MUX as it is usually called, is a simple construct very common in hardware design. The example below demonstrates a simple 2-to-1 MUX, with inputs A and B, selector S and output X. Note that there are many other ways to express the same MUX in VHDL. X less than equals A when S equals 1, else B. Latch template. A transparent latch is basically one bit of memory which is updated when an enable signal is raised. Again, there are many other ways this can be expressed in VHDL. Latch template 1. Q less than equals D when enable equals 1, else Q. Latch template 2. Process began if enable equals 1, then Q less than equals D, end if, and process D-type flip-flops. The D-type flip-flop samples an incoming signal at the rising edge of a clock. This example has an asynchronous, active high reset, and samples at the rising clock edge. DFF. Process began if RST equals 1, then Q less than equals 0, else if rising underscore edge then Q less than equals D, end if, and process DFF. Another common way to write edge-triggered behavior in VHDL is with the event signal attribute. A single apostrophe has to be written between the signal name and the name of the attribute. DFF. Process began if RST equals 1, then Q less than equals 0, else if CLK event and CLK equals 1, then Q less than equals D, and if, end process DFF. VHDL also lend itself to one-liners, such as DFF. Q less than equals 0 when RST equals 1, else D when rising underscore edge, or DFF. Processes begin if rising underscore edge then Q less than equals D, Q2 less than equals Q1, and if RST equals 1, then Q less than equals 0, and if, and process DFF, which can be useful if not all signals driven by this process should be reset. Example. A counter. The following example is an up counter with asynchronous reset, parallel load and configurable width. It demonstrates the use of the unsigned type conversions between unsigned and std_logic_vector and VHDL generics. The generics are very close to arguments or templates in other traditional programming languages like C++. Library IEEE. Use IEEE.std_logic_1164.all. Use IEEE numeric_std.all. For the unsigned type, entity counter is generic. Port Q at std_logic_vector, and entity counter. Architecture RTL of counter is signal CNT. Unsigned. Begin processes begin if RST equals 1, then CNT less than equals, else if rising underscore edge then if load equals 1, then CNT less than equals. Unsigned type is converted to unsigned else CNT less than equals CNT plus 1, end if, and process Q less than equals std_logic_vector, type is converted back to std_logic_vector, end. Architecture RTL. More complex counters may add if, then, else statements within the rising underscore edge else if to add other functions, such as count enables, stopping or rolling over at some count value, generating output signals like terminal count signals, etc. Care must be taken with the ordering and nesting of such controls if used together, in order to produce the desired priorities and minimize the number of logic levels needed. simulation only constructs a large subset of VHDL cannot be translated into hardware. This subset is known as the non-synthesizable or the simulation-only subset of VHDL and can only be used for prototyping, simulation and debugging. For example, the following code will generate a clock with a frequency of 50 MHz. It can, for example, be used to drive a clock input in a design during simulation. It is, however, a simulation-only construct and cannot be implemented in hardware. In actual hardware, the clock is generated externally. It can be scaled down internally by user logic or dedicated hardware. Process begin CL chi less than equals 1, wait for 10 ns, CL chi less than equals 0, wait for 10 ns. End process. The simulation-only constructs can be used to build complex waveforms in very short time. Such waveform can be used, for example, as test vectors for a complex design or as a prototype of some synthesizer logic that will be implemented in the future. Process began wait until start equals 1, wait until start is high for I in 1 to 10 loop, then wait for a few clock periods. Wait until rising underscore edge, end loop, for I in 1 to 10 loop, write numbers chapter 1 to 10 to data 1 every cycle data less than equals to underscore unsigned, wait until rising underscore edge, end loop, wait until the output changes, wait on result, now raise ACK for clock. Period ACK less than equals 1, wait until rising underscore edge, ACK less than equals 0, and so on. End process. VHDL simulators. Commercial. Oldic Active HDL. Cadence Incisive. Mentor graphics models. Special versions of this product used by various FPGA vendors e.g. Altera, Lattice, Synopsys VCSMX, Xilinx Vivado. Based on ISM from the previous IS toolchain. Xilinx Sync. Other. Boot. From free-range VHDL based on GHDL and GTK Wave. GHDL from ghdl.free.fr. Newer versions available SourceForge. VHDL Simile. Miscellaneous EDA utilities. Free VHDL Parser, VHDL2 Verilog, VHDL2 Exact and many other utilities. EDA Playground, free web browser-based VHDL IDE. Nick Gasson's VHDL compiler, free HDL by Edwin Naroska.